Dear students, in this video we will talk about electrocyclic reactions. We have already discussed about electrocyclic reactions in our previous lecture, and they are reversible reactions. They can be electrocyclic ring opening, or ring closing reactions. During ring opening, sigma bond is broken and pi electrons move in a cycle. So now we see Woodward Hoffman rules. We follow a table for this. Number of electrons, pi electrons, and conditions of the reaction, because we know that electrocyclic reactions can be initiated by thermal conditions or photochemical conditions. So thermal or photochemical. We can also use the symbols here. This stands for thermal, heat, and heat provides the activation energy, and this is photochemical. And here would be process, here again thermal, photochemical. And under thermal conditions we will have conrotatory process. Conrotatory means the orbitals move in same direction, and this is disrotatory, which means the orbitals move in opposite direction, and when they move in same direction it can be clockwise or anti-clockwise or clockwise or counterclockwise. So we will discuss it with some examples as well. And here disrotatory, and here conrotatory. Okay, now we first explain the table. In this case we have a number of pi electrons here, which can be 4n, and n can be 0, 1, 2. However, when n is 0, it means there are 0 electrons. So of course that cannot be the case. Therefore it can be, n can be 1, 2, 3 for example, and when n is 1, electrons would be 4, 8, 12 and onwards. So here n can be 1, for example 6, 1, 2, 3, n would be 1, 2, 3 and onwards. And when n is 1, we will have 6, 4 plus 2, and then 10, 14 and onwards. We can also remember the number of pi electrons here by number of electron pushing arrows. For example, for this 4, if we have 4 pi electrons, how many electron pushing arrows we would require? 2 electron pushing arrows, because 1 electron pushing arrow shows the movement of 2 electrons. And for radical reactions, of course, we have single-headed arrow which show the movement of one electron. Therefore, here we can use the number of electron pushing arrows which can be even or odd. For example, for 4, 8 and 12, even electron pushing arrows would be used. Even number of electron pushing arrows. And for 6 pi electrons, we will have 3 electron pushing arrows. So for 6, 3, 10, for 10, 5, for 14, 7. It means odd number of electron pushing arrows. So here we can remember by number of electron pushing arrows if they are even or odd. And in general, there are two possibilities for pericyclic reactions. The electron systems fall within two categories, 4n or 4n plus 2, and number of electron pushing arrows can be even or odd. Okay, if electron pushing arrows are even and reaction is thermally initiated, under thermal conditions the process would be conrotatory. Means both the orbitals would move in same direction. These directions can be clockwise or counterclockwise. And if the reaction is initiated by light photochemical conditions and the number of electron pushing arrows are even, the process would be disrotatory. And same for odd electron pushing arrows, under thermal conditions the process would be disrotatory, and under photochemical conditions the process would be conrotatory. Now we see some examples to elaborate Woodward Hoffman rule. Okay, now to elaborate the stereochemistry of molecules, we take the example of this molecule. And here we can see there are two methyl substituents on a chiral carbon, and they are both on the upside of the plane. Now in a ring opening reaction under thermal conditions, this bond would shift here and this would shift here. As a result, we would get this one. Now where would these two groups lie? We have to see the process. Here we have two electron pushing arrows, means we have even number of electron pushing arrows, and the reaction is being initiated under thermal conditions, so process would be conrotatory. Now both the substituents or orbitals would move in same direction. In order to elaborate the stereochemistry of this molecule, we will take this model. In this case, both of the thumbs are representing the methyl groups upwards. So both of the methyl groups are on the upper side because the chiral center is showing the methyl group on the upper side, so above the plane. So both the methyl groups on the upside and the process is conrotatory. It means that both methyl groups would rotate in same directions. So if we rotate it like this, both move in same direction, which is counterclockwise. So one is coming inside of the diene and one is coming on the outside of the diene. And if we rotate it clockwise, again one is coming outside and one methyl is coming inside. So we can now write the stereochemistry. This is inside, this is outside. And what is inside, what is outside can be taken by this example. These both substituents are on the inside of molecule and these are pointing towards the outside of the molecule. So this is inside, this is outside. So we can see it once again. We have a molecule with the methyl groups pointing above the plane. So both the methyl groups are above the plane, and when the process is conrotatory, both would rotate in same direction. For example, like this one, so one is inside and one is outside. This is one is inside and one is outside. So I hope this is clear to you. Now we see another example. Okay, in this case we can see that the process again is taking place under thermal conditions and requires two electron pushing arrows. So the process would be conrotatory. There is a keyword also, even thermal cone. If you remember it, even thermal cone, we can remember the table with more ease. So in this case we have even number of electron pushing arrows and the process is thermal, so the process would be conrotatory. So again we draw the structure of diene, and now we see where the substituent would be drawn. For example, one is above the plane and one is below the plane, and the process is conrotatory, so both would rotate in same direction. For example, this one, so both would come outside or both would come inside. We can see once again, one is above the plane, one is below the plane, methyl groups, and when we rotate it, for example clockwise, both are outside, and if we rotate it counterclockwise, both would come inside. So we have the possibility of this, both pointing outside or both pointing inside. But of course this would be major product, because due to steric problems, steric hindrance, it would be if formed minor product. So these are the examples with ring opening reactions. Now we see the example of ring closing reaction. For example, if we have a molecule like this and this undergoes ring closing under thermal conditions, and for ring closing reaction we have 6 pi electrons, means 3 electron pushing arrows are required for this reaction, and we will get cyclohexadiene as product. This would be derivative because we have 2 methyl groups as well. And now we will see the from the table that which process it would be. So these are 3 electron pushing arrows, means odd number of electron pushing arrows, so we will have this category. And thermal conditions, the process would be disrotatory. Okay, and now we see what would be the stereochemistry of the methyl groups, and we can see both of the methyl groups in the triene are pointing outwards, so it means both are like this, both are pointing towards the outer side, and the process is disrotatory, so one would come counterclockwise and other would come clockwise. As a result, both of the methyl groups are above the plane. So this would be the stereochemistry of the product. And because this molecule has a plane of symmetry, so this is meso molecule. Now we see another example. In this case again we have 3 electron pushing arrows for a ring closing reaction. Reaction is thermal, and we get cyclohexadiene, and now we see the stereochemistry of the substituents. Again, this is outside, this is outside, and this is inside. One methyl group is pointing outside and one methyl group is pointing inside, and the process in this case is odd number of electron pairs, thermal condition, disrotatory, so both would move in opposite direction. So one is inside, one is outside, if this moves this side, this would move this side. So one is pointing upwards and one is pointing downwards. One is above the plane, one is below the plane. So we will have this stereochemistry, and the process is disrotatory. So I hope these examples are clear, and in these examples we have studied the stereochemistry of the products using Woodward-Hoffman rules. Now we see how Woodward-Hoffman rules can be applied to molecular orbital diagrams in ring closing reactions, for example. So this is 1,3-butadiene, and it undergoes cyclization under thermal conditions. We get this would shift here, this would shift here, and the process is con-rotatory, even thermal con. Okay, we have 4 pi electrons, 4 sp2 carbons, and 4 p orbitals, p molecular orbitals, and 4 p atomic orbitals in each molecular orbital. We do the shading because this is ground level molecular orbital, so it would be maximum bonding interaction. Here we have one node. As we move up the order in molecular orbital diagram, the nodes increase as the energy level increases. So here is one node, here would be 2 nodes. And here we would have 3 nodes. This is pi 1, pi 2, pi 3 star antibonding, pi 4 star antibonding. And if we see the electron diagram, pi electron diagram, because here we are concerned with pi electrons. So 2 pi electrons, 2 pi electrons, 4 pi electrons. So this is HOMO and this is LOMO. So the reaction is being taken place under thermal conditions, so we will have this HOMO orbital for ring closing reaction. So we can use this one. And in this, these are on the shaded on the above side and they are on the below side. Now we see the process is con-rotatory, so they would move in same direction, either clockwise or anti-clockwise, to make a sigma bond. So it would move here and this would also move in same direction. The direction of both the arrows is same. If we see, the circle is completed like this. So if we draw the arrow like this, above half, this is also clockwise direction, this is also clockwise direction. So both of them move in clockwise direction. So under thermal conditions and con-rotatory process, a sigma bond is being formed and we get the cyclization. So this is the ring closing reaction of butadiene under thermal conditions. Now we see the ring closing reaction of butadiene under photochemical conditions. Under photochemical conditions, we will use light and cyclization would take place. And what light does different to heat is that it promotes one electron to higher energy level, so a new HOMO is formed. So one electron is excited and a new HOMO is formed. So this is HOMO orbital now, and this is LOMO. This is under thermal conditions and this is under photochemical conditions. So this is HOMO. So in this case we will use this orbital, and if we see even number of electron pushing arrows, photochemical conditions, and process is disrotatory. So we will take this orbital and we will shade accordingly. This is symmetric, this is antisymmetric, this is symmetric, this is antisymmetric. Symmetric orbitals have the symmetry in the middle as well as on the first and last lobes of the orbital. So this is symmetric orbital we are taking here, and we see that this process is disrotatory, so both of them would move in opposite directions. If one moves in clockwise direction, other would move in counterclockwise direction, and as a result of this photochemical reaction, the ring closing would take place and a sigma bond would be formed. This process is disrotatory. So I hope this is all clear to you. Now we see one more example. In this example, we would like to see the ring closing reaction of 135 hexatriene under photochemical conditions, and this would shift here, this would shift here, this would shift here, and as a result we will get this one. And here we have 6 sp2 carbons, so means 6 p orbitals and 6 molecular orbitals. Okay. Each molecular orbital would have 6p atomic orbitals, and here all would be shaded to show maximum bonding interaction. And in the upper level of energy of molecular orbital, we will get a node, and it is antisymmetric, so here would be one node. Again 2 nodes, so 3 nodes, and then 4 nodes. Five nodes. This is pi 1, pi 2, pi 3, pi 4 star antibonding, pi 5 star, pi 6 star. And under normal conditions, thermal conditions, we have 6 electrons with HOMO, this one. So this is HOMO under thermal conditions, and this would be LOMO. And under photochemical conditions, one electron would be excited. This is HOMO. This is LOMO. And because the reaction is taking place under photochemical conditions, we will take this orbital. So this one. And if we see the process, odd number of electron pushing arrows and photochemical conditions. Odd electron pushing arrows, photochemical conditions, and process is conrotatory. So it would move here, this would move here, and under photochemical conditions and conrotatory process, the sigma bond would be formed. So this is all about today's lecture. I hope everything is now clear to you. If you find any question or confusion, please leave your questions in comment box. Thanks.